As we start section 14.4, let's recall the function that we started the last section with. So we started off looking at the partial derivatives of the function 5 minus x squared over 9 minus y squared over 4. And we found our partial derivatives, though we didn't actually name them at that point. Or at that point in the last video, we hadn't quite named what a partial derivative was. But we found the partial derivative in the direction of x at the point 3,2 is negative 2/3. And the partial derivative of f with respect to y at the same point is negative 1. So these are the partial derivatives at the point 3, 2, 3. If we were to plot those, so we go ahead and actually plot that surface. That should be an x. Remember we had our elliptic paraboloid. You can go ahead and make that actually a lighter color. Go ahead and put the point 3, 2, 3 on there. So I got this point A that's on our surface. And then using those particular partial derivatives, we are able to get tangent lines to our surface. Specifically, if we looked at the planes, y equals 3, or sorry, x equals 3 and y equals 2, those are vertical planes that pass through that point that are parallel to our coordinate planes. We could look at the intersection to actually see what curves we're really talking about. Oh, it just didn't make it as dark as I expected. Come on, give me those curves. So we have these two curves that pass through our point that are on the surface that are parallel to our coordinate axes. Each of those gives us a tangent line. So we get tangent line. I'm just using the fact that I know what the point is. I can kind of ignore the coordinate when I'm actually creating my equation for our line. And I'm just going to go ahead and use parametric equations to actually plot them. So our first one will be t2. So here I'm keeping the y value constant at 2. But then I'm using the fact that the derivative in the x direction is negative 2/3. And I already calculated the b value to be plus 5. And what did... Oh. That should be a t, not an x. There we go. Stop making my lines really thin. I want them to show up better. There we go. You can do the same thing in the y direction. In fact, the equation here is a little bit simpler. Just negative t plus 5. And again, I need to make it thicker. There we go. So we have these two tangent lines to our surface that go through that point. But of course, there's a lot of other tangent lines possible. And how do we describe all of them? Well, these two lines here, they determine a plane. There's a plane that is tangent to our surface at that point, and that plane will contain all other tangent lines to the surface at that point. Such a plane will, of course, be called the tangent plane to the surface. So let's figure out how we might find the equation of this plane. We've already talked about how to look at equations of planes. So how would we get the equation of a tangent plane? So recall that our general equation of a plane is something like ax plus by plus cz equals d. Or if we actually know that a point, if say we know that the point x naught, y naught, z naught is on the plane, we can in fact write this as a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. Let's actually rearrange this to solve for z, or at least solve for the z minus z naught. So we have c times z minus z naught is equal to negative a times x minus x naught minus b times y minus y naught. I'm going to assume here that c is not 0. If c was 0, we would be working with a vertical tangent plane. Just like when we were working with functions of 2 variables, vertical tangent lines were kind of an issue. Here, vertical tangent planes would be kind of an issue as well. So we're just going to assume that we're in a nice simple situation where we don't have a vertical tangent plane. So we can divide by the c. So that z minus z naught is equal to, I'm going to rename negative a over c to just be a little a. And I'm going to rename negative b over c to be a little b. And I want to find out what is a little a, what is a little b. Now, we've been talking about looking specifically at when we're parallel to one of the coordinate planes. Let's actually try that out here. If we say that we're going to be parallel to the xz plane, we're going to be saying that y is a constant. If y is our constant value of y naught, and we plug that into our equation here, then we have z minus z naught is equal to a times x minus x naught plus, well, now this is just 0. So if we're just looking at that particular plane, then we just have this equation for a line. And what is this equation for a line? Well, this is just really the point slope form for a line. And this is the tangent line. So this a, the slope of this line, is actually given by the derivative of the curve that we get when we specify that y is a constant value of y naught. Or in other words, this a is really just the x partial derivative at x naught, y naught. Similarly, if we look at the other direction where we specify that x is a constant x naught, we do the same kind of thing. We still have z minus z naught over here. This time the x minus x naught becomes a 0, and we're left with b times y minus y naught. And for the exact same reasons, this is in point slope form for a tangent line that's parallel to the yz plane. And so the b is our derivative. It's just the partial derivative of f with respect to y at the point x naught, y naught. Therefore, we get a pretty easy equation for our tangent plane to the surface. We just get to stick the partial derivatives into our formula. So z minus z naught is just the partial derivative with respect to x times x minus x naught plus the partial derivative with respect to y times y minus y naught. It's just that simple. And note that this here is just a number. This here is also just a number, where it's not. It may actually even look more complicated than it really is. But if we go back to our original example here, we have our partial derivatives at the point. We know what that point is. This is our x naught, y naught, z naught. So we can just write down our tangent plane. We have z minus our z naught is 3, is equal to our derivative in the x direction, negative 2/3, times x minus our x naught, which is another 3. Then we have plus the y derivative, so a negative 1 times y minus our y naught is 2. And that's the equation of our tangent plane. Of course, we can go ahead and simplify it a little bit. Kind of, let's pull out the x and the y terms here, and then combine all the constants. So we have a 3 that's going to be moved over here. This will be a positive 2, and in fact, this gives us another positive 2. So in fact, we get plus 7. And if we actually plot that plane, so z is equal to negative 2/3 times x minus y plus 7, it is exactly the plane that we expected to get. It is tangent to that surface at that point. It contains the two tangent lines we already knew about our surface, and it will contain every other possible tangent line as well. Let's do a couple quick examples of this process. So here, this is actually not too dissimilar to what we just did. We have an equation z equals a function of x and y, a particular point on the surface, and we actually want to find a tangent line or tangent plane to this surface. And I'm not going to plot this one. If you want to, you can. But all we really have to do is look at what are our partial derivatives. Partial derivative of this function with respect to x. Remember here we're keeping the x, or we're keeping the y constant because we only differentiating with respect to x. So here, 2x squared with respect to x is going to be a 4x. Y squared is being treated as a constant because it doesn't have any x's in it. Same thing with negative 5y. So our partial derivative with respect to x is 4x. Of course, we are mostly concerned with what happens at the point 1, 2, negative 4. So really, we're just going to immediately plug in the 1, 2 for x and y. Of course, there's no y's here, but when we plug in 1 for x, we get a 4. Now we look at for y. 2x squared, when we're differentiating with respect to y, is 0. There's no y values in there. Y squared becomes a 2y. Negative 5y becomes a negative 5. And we're immediately going to plug in 1, 2. Of course, there's no x's here, but when we plug in 2 for y, we get 2 times 2 is 4, minus 5 is negative 1. And then what do we do with those? Well, we just use our formula. We have z minus z naught, so z plus 4, is equal to the x derivative of 4 times x minus x naught. X naught is 1. Plus our y derivative, so negative 1 times y minus y naught, but y naught is 2. And that's our equation. And we could leave it like that. I think GeoGebra is or not GeoGebra. I think the WebAssign is perfectly fine with those. But if it specifies that that has to be in the form of z equals something, we can easily go ahead and expand things out. We get a 4x. We have a minus y. If we combine all of our constant terms, we have a negative 4 here. We have a plus 2 here. And we have a 4 that's going to become a negative 4 over on this side. And so ultimately we get a negative 6. And that's the equation of our tangent plane. It's just that simple. Of course, the derivatives themselves might be a little bit more complicated overall, but the process of this is always going to be the same thing. Let's look at problem 6 instead. Here, of course, we are going to have to do a little bit more work in the actual differentiation, but it's still not that complicated of a problem. Here, z is equal to the natural logarithm of x minus 2y. If we differentiate this thing with respect to x, we have to use the chain rule. Derivative of the natural logarithm of something is 1 over what's inside. Then we have to multiply by the derivative of the inside. But keep in mind we are differentiating with respect to x, so the derivative of x minus 2y is a 1, because x becomes a 1, and negative 2y is just a constant, so it becomes a 0. So in fact, we don't even have to multiply by anything here. If we go ahead and immediately plug in our point, our 3, 1, 3 minus 2 times 1 is just a 1, so we have 1 over 1 is 1. The y direction is a little bit more interesting, but we still start off with the same thing. We're still taking 1 over the inside for a derivative of the natural logarithm part. It's the derivative of the inside that we have to multiply by that's a little bit more interesting. Derivative of the inside with respect to y this time, the x is a 0, because there's no y's there, but the derivative of negative 2y is a negative 2. So we're going to multiply that by negative 2. We go ahead and plug in our point, our 3, 1. In fact, the bottom is exactly the same thing, so we still get the same 1 on the bottom, but now we have a negative 2 on top. We can go ahead and then plug those into our formula. We have z minus z naught, but z naught here is a 0, is equal to 1, the x derivative, times x minus x naught, which is 3 this time. We have plus the y derivative, times y minus y naught, which is a 1. And then, of course, we can go ahead and simplify this if we prefer. We have x minus 2y, and then the negative 3 and a plus 2 gives a negative 1. So again, pretty simple process as long as we know how to take the derivative. And the only reason derivatives here are even a little bit complicated is the fact that we have to remember to keep the other variables constant. So most of the difficulty is from last class, not from this class. But you can go ahead and take a look at those. You can graph those and see whether or not they match up like you expect them to. In fact, problem 6 looks kind of interesting because that tangent plane actually works for more than one point. Actually, is it kind of tangent to the surface of the entire line. So if you want to take a look at that, it's kind of fun. But let's go ahead and move on. So now that we can talk about the tangent plane to a surface and we know how to use partial derivatives to get it, the next question is how well does this tangent plane agree with the surface? In most circumstances, the tangent plane will approximate the surface better than any other plane. Let's take our example from our problem 1. So we have this quadratic surface here, and we found this tangent line. We are going to treat this tangent line as a function. So we're going to look at some function L of xy is equal to 4x minus y minus 6. And we're going to compare it to our original function, f of xy. And here, remember, we have 2x squared plus y squared minus 5 of y. And we want to see how close these are to each other. Now let's go ahead and actually plot those. So here we put in 2x squared plus y squared minus 5y. It's another elliptic paraboloid. Probably need to move this up a little bit. Come on, there we go. Then we go ahead and put in our other function, which I called capital L. In fact, let's go ahead and even name it here. Capital L is going to be 4x minus y minus 6. And I kind of wish they chose it a different color. And we'll make this one a light blue. So that plane is a tangent plane at a point. In fact, if we could go ahead and put in that point, recall that point was supposed to be 1, 2, negative 4. And you can see that's correct. But the point is, if we zoom in on that point, let's make sure we don't move too far down. The further we zoom in, the closer and closer the surface gets to looking like that plane. And it gets even closer and closer as we zoom in. And I kind of missed my point a little bit there, but the point is that even though at a large zoom, it does actually, or if we're zoomed pretty far out, the surface doesn't really look very planar. But the closer we get to the point, it looks closer and closer to just agreeing with that plane. And that's what we want to see. We're basically allowing ourselves to use a linear function. That's what this L, the reason why I picked L here, is called a linear function because we're just dealing with these linear terms of 4x and y rather than these quadratic terms. And we're being able to find a function that closely approximates our function, the original function, that is just linear. It's called a linearization. So L here is a linearization of f at the point 1, 2. Or you could say 1, 2, 4. Or 1, 2, negative 4 if you want to. But near the point 1, 2, our original function f of x is approximately equal to our linearization. And there's no better function, no better L of xy that's a linear function that does this. And that allows us to do computations. If we know particular points, if we know stuff about if we're taking points that are close to 1, 2, we could use this to simplify our computations. If we say we want to know what is f of 1.1, comma 1.9. This is a point that's close to 1, 2. It's not too difficult to actually go ahead and plug these values into our original function if we want to. And we can actually compute that to be a negative 3.47, though you probably want to use a calculator for that. But it's actually a lot easier, and not having to use a calculator for it, to go ahead and plug those numbers into our linearization. We have 4 times 1.1 minus 1.9, and then a minus 6, and that's exactly equal to negative 3.5. So these are very close, and they would be closer if our point was even closer to 1, 2. So if you put it in 1.001 and 1.99, this would be an even closer approximation. And of course, the linearization is a lot easier to compute. And that would be even more impressive, I guess you could say, if our function didn't start off as a quadratic. If we had a more complicated function, if we were dealing with logarithms or exponentials or trig functions, things that are actually a lot more difficult to work with if you don't have a calculator, this would be an even better. It'd be even better to do the computations using a linearization. We can also write our linearizations as what we call differentials. Recall that a differential So if we have a function of one variable, y equals f of x, the differential of this function is dy, which is the derivative of f with respect to x, times dx. And we use these back in Calc 1 to perform approximations. Basically, if we had a small change in our x value, we can compute how big of a change of our y value we would expect by using this derivative. We can do the same thing with a function of two variables. So if we say z is equal to f of xy, we get the equation that dz is equal to the derivative of f with respect to x times dx plus the derivative with respect to y times dy. So we actually get multiple terms, but we should expect that, because really all we're doing here is kind of writing down our tangent plane. So here, the dz is an approximation for z minus z naught. We still have our derivative with respect to x. Dx is actually a stand-in for x minus x naught. It's our difference in x's. Then we have our derivative with respect to y. And then dy is our stand-in for y minus y naught. It's our difference in y's. So in fact, we will use the formula x minus x naught to actually compute dx in general, and same thing with dy. And then dz is just going to be an approximation for z minus z naught. So what we're really doing here is we're approximating our z values by the tangent plane. It's just another way of actually organizing our work. In fact, we can also do this with functions of three variables. If we say w, just giving it a name, is a function of x, y, and z, then we get this equation. This time the book didn't actually name the function, but it's just using this other notation over here for our partial derivatives. So dw, the differential of w, is the derivative with respect to x times dx, plus the derivative with respect to y dy, and the derivative with respect to z dz. And in fact, this generalizes to as many variables as you want. You just have to keep adding in more terms. But the point here is that these give us a way to actually approximate the value of a function around a point that we actually know already. So let's look at an example of that. Here we're being asked to find the differential of this function, and while they don't ask us to actually approximate anything using that differential, well, let's go ahead and do that once we've figured out the differential. Now, of course, that does mean that we need to know what are the partial derivatives. What is the partial derivative of this with respect to x? Well, we have to use the chain rule, of course. So derivative of the square root of something is 1/2 times what's inside there to the negative 1/2, and we'll simplify that in a moment. The inside is x squared plus 3y squared. Then we have to multiply by the derivative of the inside. But we are differentiating with respect to x here, so x squared becomes a 2x. 3y squared becomes 0 because there's no x's. And then we can actually go ahead and simplify this. The 2 cancels out with the 1/2. The negative 1/2 power here means that this is a square root on the bottom. So actually I'm going to go ahead and write it that way. We're going to have this x over the square root of x squared plus 3y squared. We do the same thing for y. In fact, the beginning is exactly the same because we hadn't worked with the inside function yet. But now the derivative of the inside function, the x squared goes away. The 3y squared becomes a 6y. We go ahead and simplify that just like we did before. This time we get a 3y on the top, and we still have the square root on the bottom. So our differential, our du, is this partial derivative times dx. So we'll go ahead and just write that in there. That partial derivative is times dx. We have this partial derivative times dy. And that's our formula for our differential. In fact, one thing you might do here, if you to make it look a little nicer, since everything is over a square root of x squared plus 3y squared, let's just go ahead and pull that out. We'll have a x dx plus 3y dy over the square root of x squared plus 3y squared. It's a nicer way of writing it. Now let's use this formula to actually approximate a particular value of the function. So in order to do that, we already need to know a particular point on this surface. So we're going to approximate things around the point 1, 1, because we know that u of 1, 1 is equal to 2. Because if you put 1 and 1 in here, you get square root of 4. So we need to know one value pretty well. Then let's look at a point that's a little bit closer, or look at a point that's close to 1, 1. I'm going to look at what is u of 0.9, 1.1. What is that thing? Note here that our dx, this is our difference in x's, is going to be our new x minus our old x, so 0.9 minus 1. Let's actually go ahead and write that out. This is a negative 0.1. Our dy is our 1.1 minus this 1. So it's going to be a positive 0.1. This negative is actually kind of important here. We need to make sure we take that into account. Our du, coming from this, we're plugging in the easy point. We're plugging in the 1, 1 in for our x and y. So our du in this case, this is a 1 times dx plus a 3 times 1 times dy. On the bottom, we have the square root of 1 squared plus 3 times 1 squared. This is the square root of 4. So we get a 2 on the bottom. That's our formula for the differential at the point 1, 1. And now we're going to use it using these particular values for dx and dy. So negative 0.1 plus 0.3, because that's 0.1 times 3. Divide that by 2. The top actually is a negative, when we subtract the 0.1 from the 0.3, we get a 0.2. And when we divide that by 2, we get a 0.1 again. That means that the value for 0.911 is approximately equal to our value from 1, 1, which is 2, plus that differential of 0.1. So it's approximately equal to 2.1. The exact value, in fact, since we do have calculators, we can actually figure out what that exact value is actually closer to 2.107. So it's pretty close for something that would have been really complicated to do by hand, even though obviously nowadays we can kind of cheat with the calculators. But at the very least, we have a way of dealing with, of actually doing this approximation by hand. None of this really required us to use a calculator to come up with this 2.1, and that's a pretty good approximation for our value if that's all we're looking for. And it can actually be useful even with computers and calculators to be able to approximate a particular function around a particular point for a bunch of points in that region. Maybe I'm not really saying that very well, but it's a way for it to kind of save the computer from doing a lot of work to do something that can just be done by an approximation, and can speed programs that rely on that kind of stuff. Anything like with graphics or stuff like that, they can get by with some approximations and not have to waste a bunch of time doing computations that won't really matter. Now I'll leave this video off with one last example. This actually comes from example 6 in the book. This is another way of using differentials and shows why we might use these in a three-dimensional situation. So here we have a rectangular box. Really easy kind of idea here. And that wasn't really drawn well, but whatever. The point here is that our box is measured to have our particular values here of x, y, and z. X is supposed to be 75 centimeters, y is supposed to be 60 centimeters, and z is supposed to be 40 centimeters. But we're working with the real world, so our measurements may not be exact. Our measurement may be off by, they're saying here, our error in measurement is no more than 0.2 centimeters for each one of these. We're wanting to know how far off from the true volume of the box we would get if we use these values of x, y, and z. Now, of course, we're using the formula for volume of volume equals the product of our x, y, and z. If we're wanting to find out how far off, we're basically looking at what is the possible value of dv. We're taking the differential of this thing. Well, now we're taking, remember the formula for that, we take the partial derivative of x, y, z with respect to x. Remember there, y and z are treated as a constant, so it's a constant times x. And so the derivative of constant times x is just the constant. So we have yz times dx. We do the same thing, we differentiate with respect to y. That's going to be an xz this time, times dy. And then the derivative with respect to z, that's going to be xy times dz. Okay, now we go ahead and put in our values. So we're kind of considering the worst case scenario and saying that dx, dy, dz are all this 0.2. In reality, we're basically saying that all those are no bigger than 0.2, but here we don't know, they could be up to that. So that would be the worst possible situation. We go ahead and put our values in. We have 60 times 40 times 0.2. We have 75 times 40 times 0.2. And then we have 75 times 60 times 0.2. Or in other words, when we multiply all this out, we get 1,980 cubic centimeters, which might seem like a lot, but it's actually not really as big as it might seem. If we use these values to put in for v, so basically 75 times 60 times 40, we actually get a quite big number of 180,000 cubic centimeters. So what we're really doing is we're getting a rather small value compared to what the measurement value would be. And so in general, it might be better to look at what we call the relative error So dv would be the absolute error, but we want to see what is that error relative to the value of the function. We put dv, the absolute error, over the actual value. So 1980 divided by 180,000, which is going to be about 0.011, or in other words, it's 1.1%. So we can have an error of about 1.1%. Or actually, you could say up to that amount, because our errors in measurement were up to 0.2. So that's a way of actually using differentials, even if we're not really looking at a graph, and we can look at an example where we actually have more than two variables. Alright, so I'll leave that off here. There will be another video. It'll be a little bit more on the theory side and less on the actual computation, but it is kind of important. We've actually been assuming things here that you might not have expected. So do take a look at that. We want to make sure that we know what we're doing, making sure that what we're doing is correct. So join me in the next video. So I'll see you there.